Here we go. Alrighty, welcome everybody to Hype Week of the Quantum Ethics Reading Group. I'm excited to present Indy, who's going to be discussing quantum applications to the environment and whether or not they may be overhyped. And with that, I'll hand it over to Indy. Go ahead.
So as we move into the stage of noisy intermediate scale quantum computing, there has been a lot more focus by researchers on finding useful applications for quantum computing. And one of those potential applications has been to use quantum computing to solve the problem of climate change. So I think a very good question to ask is, can quantum technology help defeat climate change? And there are a couple of subtler questions embedded in this larger question. For example, is this use case of quantum computing a hyped up use case? Is this even a practical use case of quantum computing? And whether this use case is hyped up or not, we'll discuss that slightly later. But with regards to practicality, I think everybody in this room generally agrees that climate change is a pressing issue that needs to be solved. So if quantum computing can contribute any solutions at all to the problem of climate change, I think that just makes quantum computing a practical use case with regards to solving the problem of climate change. So the paper actually presents 4 questions that they say people working on using quantum computing to solve environmental problems should ask themselves. And these questions are also useful questions to provide us a lens through which we can understand the paper we're reading today. So the first question is, can quantum computing provide unique solutions to environmental problems? And the second question is, are these solutions timely and equitable and can overcome the scaling issues that quantum computing currently faces? And the third question is whether quantum computing is going to worsen existing energy and resource usage, as well as increase damage to the environment. And the last question that the paper says we should think about is, what are the policies that we should consider to advance quantum computing and environmentally relevant applications of quantum computing, as well as ensure equitable access? So with regards to the first question about whether quantum computing provides a unique solution, well, there are actually several big companies that do believe that quantum computing does provide a unique solution. For example, McKinsey and Forbes, and there's even other institutions like the government of Canada that believes that quantum computing is going to help, and we should, solve the problem of climate change. And even TQT, which is actually an extension of the IQC, they are all organizations that believe that quantum computing has the potential to help design innovative solutions to the problem of climate change. And these corporations are thinking about quantum computing positively impacting technologies like carbon capture, improving battery design, and enhancing material sciences. And we can actually step back and even think about this in more academic terms. And it was Feynman who originally proposed that quantum computers should be uniquely suited to efficiently simulate quantum systems over classical computers. And over here, he's arguing that chemistry simulations should be better handled by quantum computers than classical computers. And so can we safely say that quantum computing can provide unique solutions to the problem of climate change? Actually, it's a bit more complicated than that. And the paper actually explains that just because quantum computing is improving and working on scaling up, that doesn't mean that classical computing isn't innovating as well. For example, think of the protein folding problem. We know that there are deep neural networks that can efficiently solve the problem of protein folding, and even quantum physics problems like learning electron interactions. They have also been successfully tackled by deep learning. So it is possible that there are other solutions in the realm of classical computing that can provide the same solutions that quantum computing can. And so the answer to whether quantum computing can provide unique solutions is really a nebulous yes, with a question mark. And so now we move on to the second question of whether quantum computing solutions are timely and equitable and can overcome scaling problems. So when we want to talk about timeliness and equity, we should be talking about where we are right now with regards to quantum computing. And so I actually think that we're moving kind of into the stage of noisy intermediate scale quantum computing. And obviously the goal is fault tolerance. So now let's take a look at some of the proposed applications that quantum computing could be used for. For example, nitrogen fixation. And I'm sorry that it's obscuring the title of the paper, but the idea is that we could use quantum computing to better understand the reaction mechanisms behind nitrogen fixation, which can help us improve capture of nitrogenous greenhouse gases. And with regards to battery design, the idea is that if we could simulate key properties of batteries better, we could design better batteries that could be more efficient at storing energy. And thank you. With regards to the technology of carbon capture, they're arguing that if we can find better catalysts that can enhance carbon capture, we could better design more efficient technologies surrounding carbon capture. And so we have all these potential applications of quantum computing for the environment. And actually, possibly, there are more, but these are the main ones. So talking about whether these are timely solutions, well, these applications for climate change actually require fault-tolerant quantum computing. And with how pressing climate change is as a problem, we don't have 30 years to wait for fault tolerance. There are also other factors like regulation and wider market acceptance that can worsen the issue of timeliness. For example, you can design a better fertilizer using a quantum computer, overcoming scaling issues. We can assume that, sure, but then it needs to undergo regulation from the government, which is going to take a couple of years to process. And even then, maybe the general populace might not accept or adopt these new solutions. And so the other,
additional point, if you go back to the slide related to carbon capture, this is a paper by Matthias Treuer, and they actually spend some time. They have a section in their paper where they discuss that near-term quantum algorithms, like the variational quantum eigensolver, are not capable of doing what their algorithm is proposed to do.
Yeah.
So that's just a particular example. And that TQT slide, there's currently a competition here at Waterloo where they're asking people to submit new applications of quantum technology to address climate change. So maybe something new will come. But this idea that we are going to address climate change in the near term is entirely overblown.
Exactly. And the other question about equitable access to these solutions, well, I think we all can agree that currently quantum computing resources are focused mostly in the global north. Think America, think Europe, think Canada. Whereas climate change is a problem that affects the whole globe, even the global south. And so with regards to whether these nations are going to be able to access these quantum solutions to climate change, I think that they're probably not going to be able to, because countries are going to monopolize these quantum computing resources with regards to solving climate change. And so with regards to whether quantum computing can provide timely solutions in an equitable fashion, the answer is probably not. And so we can move on to asking ourselves, will quantum computing worsen existing energy and resource usage? And with this, actually, a lot of the conversation kind of has been around how quantum computing can accelerate like computations with regards to, say, quantum systems and energies and stuff like that. But they kind of miss out on the fact that currently, quantum computing needs to be cooled to really low temperatures in order for them to function effectively. And that first kind of picture is just a picture that describes the ranges of temperatures that existing quantum hardware work effectively in. It's like it goes from left is cold and then right is hot, and then they give the ranges there. So these are pretty low ranges, and actually cooling as an energy sink is actually a lot higher with regards to the savings you can get from any computational advantage in whatever algorithm you're trying to do. So we have to address the issue of cooling as an energy sink if we want to use quantum computing as a solution for the environment.
just
Yeah.
just so that I understand, is a good model, like you compare your two computers. You got
Yeah.
your giant supercomputing cluster.
Yes.
You got your quantum computer.
Yeah.
Supercomputing cluster takes 10 hours to do the job. It takes a ton of energy to run that thing.
Mhm.
Maybe the supercomputer can, or the quantum computer can do it a lot faster, but because it requires all that cooling,
Yeah.
maybe you still have a net loss in terms of energy
Exactly.
efficiency.
Exactly.
Is that what we're talking
Yeah, exactly. Because there's been research that's shown that when it comes to computational advantage and like solving these problems faster, sure, that does give you some energy saving, but it is dwarfed by the energy that you're going to be using to cool these quantum systems. And so, and like to get them to those cold temperatures is going to use a lot of energy. To keep them at those temperatures is also going to use a lot of energy. And so overall, it's just a net loss.
Just a final point about this chart. 0 Kelvin is the coldest temperature. So the warmest one on this scale is 10 Kelvin.
Oh, wait. What's the room temperature is 270
Yeah.
something. So this is very low for the non-physicists.
Superconducting qubits require a temperature colder than the vacuum of space, which is 2.7 Kelvin.
Yeah, it's insane. Yeah, but the scale is relevant. Yeah, that was a good point. Thank you. And it's absolute zero. I don't know what it is, but it's
coldest temperature.
I don't think it's even possible because quantum fluctuations and whatnot. But anyways, sorry, off track. But with regards to resource usage, there has been some recent discoveries about cuprous oxide, like being mined from Namibia, that could hold the key to building more efficient like quantum computing infrastructure. And that's just bad, right? We can all agree, like this study was published by the University of St. Andrews. I thought we were all done with the idea of going to Africa and mining for resources and building better quantum computers. I feel like that's like so this is another kind of example of how quantum computing could worsen existing resource usage, as well as damaging the environment through mining and stuff like that.
It doesn't help that we're going and we're damaging the environment in Namibia, and then we're bringing the good stuff back and using the quantum computer just to solve our problems up here in the global north.
Exactly. And so with regards to the question of whether we can whether quantum computing is going to worsen existing energy and resource usage, the answer is probably yes, which is bad. So that's another thing. So that leads us to kind of, oh no, I want to track this here. That leads us to our final question, which is, sorry, what are the policies that we can discuss and even actually other interventions that could better tackle and help support quantum technologies as well as environmentally relevant applications, as well as ensuring equitable access? And so this is where we can talk about policy amongst other things, like whether quantum computing is even a good use case, which I hope through my presentation has convinced you that probably not.
Let's thank Indy for a great presentation. Okay, I'm going to stop the recording now so that we can all just discuss.